For your next test review, we're going to be looking at Unit 7, investigating components of the universe. So, as usual, want to definitely go over some TEKS with you first. So let's look at this one. So 8.8a is to describe components of the universe, including stars, nebulas, and galaxies. Use models such as the HR diagram for classification. We'll talk about the HR diagram momentarily. Let's look at the next one. 8.8b. Here we go. All right. Recognize that the sun is a medium-sized star near the edge of a disc-shaped galaxy of stars, and that the sun is many thousands of times closer to the Earth than any other star. It's the only star in our solar system, friends, so it's got to be the closest. And so there's just a couple of examples there of stars. You can see that our star, the sun, is actually pretty small comparatively. But we got some others, Regal, Betelgeuse. We got Regal is a supergiant, blue supergiant, super hot, super bright. And Betelgeuse is a red supergiant, not very hot, but really bright. And we'll talk about why here. We'll review why here in a moment. So we're going to do one more TEK that we're covering in this review, and that is the EM spectrum. Explore, and this is 8.8c, explore how different wavelengths of the EM spectrum, such as light and radio waves, are used to gain information about distances and properties of components in the universe. So you have the huge waves with not a whole lot of energy, radio waves, on this side over here, and then as it moves, in this case from the right to the left, you can see that they get smaller, more frequent, and full of energy all the way down to gamma rays. So those are the big three that this test is made up of. So let's dive in and start looking at some of this information. First thing that I wanted to go over is Earth is the closest star the sun is the closest star to our planet Earth, and the next closest star is one of those Proxima stars, Proxima Centauri, about 4.3 light years away. And what's a light year? A light year is the distance that light can travel in 1 year. So, you know, our moon is about 1.5 light seconds away. The sun is 8 light minutes away, and it takes 100,000 light years to get across our galaxy. We're going to be reviewing man strategy from atoms and our chemicals units. So the mass minus the atomic number gives us the neutron, so make sure you remember that. And then reactive groups, remember group 1 is the most reactive metal, and group 7 is the most reactive non-metal. And then got to remember how to T-chart. So when you're looking at a formula, break it down with a T-chart. You have elements and atoms, and then count how many elements you have, how many atoms of each element, and then total atoms and elements, and make sure that both sides of the equation are balanced. Because remember, we have reactants yielding products. Reactants on the left, products on the right. Okay? And then we have objects in motion. What do? They stay in motion, right? Unless they're acted on by a unbalanced force. Convergent boundary moves together. And what happens when you have two plates moving together? We have mountain building. We have subduction when you're talking about, you know, oceanic and wet plate. You have subduction. We have trenches at that point of subduction, the deep, deep part. We have volcanoes. As the wet plate is being subducted, we have that magma that comes up. And so inside the mountain building, we will have volcanoes. So, and sometimes we'll have earthquakes too. So convergent boundary, STVs, remember that. Divergent boundary, moving apart. Not a whole lot that can happen here. Sometimes earthquakes. Sometimes you get a little volcanic activity. Definitely not the most synonymous with volcanic activity, but it can happen. But Underwater, we call that mid-ocean ridge. On land, we call that a rift valley. Okay, switching gears, going back into space. What's a nebula? That's right, birthplace of stars, where new stars are born. We have stellar nebulas that happen, and that's when your big, massive stars go into supernova. And then we have those clouds of gas in space that become, kind of a nursery for new stars. That'd be your nebulas that'll happen. And then you have your planetary nebula, and it's as the giant, or as the red giant is starting to shrink and contract, it gives out some dust and that type of thing, and some stars can be born in that regard as well. Galaxies, our galaxy, it's a spiral galaxy, right? The Milky Way, and it can be described as spiral, disc-shaped, and pinwheel. Look for all three on your star test. It can be described either any of those different ways, but it means the same thing. So, because galaxies are classified by shape, and that's the shape of our galaxy. It's a spiral galaxy. And then you have your elliptical, which kind of looks like like an elliptical machine would go like this. That's kind of what it looks like, an elliptical galaxy. And then you have your irregular galaxies, which really don't have any shape. Black holes. Black holes are, incredibly, the gravity is so strong that it can pull in everything, even light. So understanding what a black hole is, it's just an area that has, that can take in everything around it, even light. The sun is located in the main sequence. So when you're looking at your HR diagram here, for example, you have your main sequence, which kind of goes this direction, right? So the sun is located like right around here-ish, and then you have your giants over here, your supergiants are along the top, and you have your white dwarfs in this area. Let's talk a little bit more about the HR diagram. So as you're looking at the HR diagram, you can notice that the temperature, when you have a normal x-y axis graph, you know that things typically will increase like this naturally, but not in the case of the HR diagram. It's not the same in this case. The temperature increases as you move from the right to the left. So Betelgeuse, which would be up here, is a star that's really bright. Look at the luminosity, right? It increases as you move up. But it's cooler because it's on the right side. So you just gotta kind of look at it like this. And I like to break it off into a quadrant like so. We have your bright and cool stars in the top right. You have your dim and cool stars on the bottom right. You have your dim and hot stars in the bottom left. And you have your bright and hot stars in the top left. So that's kind of how this thing goes. And the one thing that really drives, when you look at your giants and you look at your supergiants and you really compare them, the one thing that they have in common is the fact that they're big. They're really, really big. And size in space, when we're talking about stars, that's what drives brightness for the most part. I mean, look at these white dwarfs, for example. They're super hot, but they're dim. So just some trends to pay attention to when you're talking about, and you're looking at the HR diagram. You're trying to decipher what's going on there. So star stages. We know that our star is a medium-sized star, and our next stage in our sun's life is going to be red giant, and then at that point it'll start shedding its lining, and then it will become white dwarf, black dwarf, and gone, okay? The reason why that is because our star's size is not very big. It's an average size star. But then you have the stars that have a ton of mass. We call those massive stars. And so those stars will go into red supergiant, and then from there they will supernova, right? And once it supernovas and explodes, two things will happen at that point. You have a neutron star that can happen, or a black hole that can happen. So our star will not explode because it's not that big. It's an average sized star in the main sequence. And where are we located in the galaxy? We are located halfway down one of the spiral arms. Not in the center of the galaxy, not on the outside of the galaxy, but halfway down one of the spiral arms. That's where we've figured our location is in the Milky Way. A couple other last little things you need to know. You need to remember that H fuses to He, and that's what allows our sun, our closest star, to give off energy and heat, is that nuclear fusion that's happening from H being converted to He, because those hydrogen atoms are flying around and smashing into each other, and when they do that, they convert to helium. And the last two things are the age of our universe is somewhere about 13 billion years old, we've figured. And the last thing I'll leave you with is radio waves and gamma rays. So we have radio waves, which are the largest of the waves with the least amount of energy. They don't hurt us. They're all around us, and they don't do anything to humans. They don't hurt us. They don't affect us very much. But as the wavelength becomes quicker and closer together, the energy increases. As the wave gets smaller and more frequent, the energy increases a lot. And so you start looking at microwaves. And you know what microwaves can do. They can heat things up. Can be pretty damaging. You don't want to ever get caught in a microwave. I'm just guessing. And then you look at, and then we have visible light. Don't forget Roy G. Biv, right there, located in the middle of the EM spectrum. And then we have some others, infrared and X-ray, which are very small, damaging rays. And then the last one is gamma, the smallest, highest frequency, most energy, and responsible for turning the Hulk, Dr. Bruce Banner, into the Hulk. So remember that. And that, my friends, is your Unit 7 Investigating Components of the Universe review, and we will see you in class. Thanks, guys.